Hello, am I audible now?
Yes.
Yep.
We can start the session. Okay.
Yeah. My video, I hope my video is also on. Yeah. So, just a minute. So, good morning, everyone. It is an honor and a great pleasure for me to introduce Professor Lukasz Cincio from Los Alamos National Laboratory in New Mexico. He works on quantum computing, tensor networks, and machine learning. And today he'll be talking about generalization in quantum machine learning from few training data. Really excited, and we all look forward to your talk, Professor Cincio.
Hey, thank you for a very nice introduction. Indeed, I'll be talking about generalization in quantum machine learning from few training data. Our work, I must say, attracted quite some media attention after our paper was published. But as you can imagine, journalists didn't really like our title. So it's long. There are some complicated words, right? Generalization, training data. What even is that? So they change it, and what they what they propose is this. They propose quantum artificial intelligence isn't a data hog after all. And just look at this. This is perfect, right? There are all buzzwords, right? We have quantum AI, we have domesticated pigs, right? It's just perfect. Actually, if you search that title, our paper shows up, which I'm not entirely sure if I'm happy with this, but this is what it is. So as you can see, I have many collaborators to acknowledge. So this work has been done together with Matthias and Robert, both from Caltech. It was done together with Kunal. Kunal was our summer student from our quantum computing summer school, now at IBM. It's been done together with two other or former quantum computing summer school students, Joe and Zoe, now at AWE and EPFL. Respectively, it was done with Nick, another student, as well as some Milano folks, Marco, Andrew, and Patrick. All right, so here's a plan of my presentation. I'll be talking about quantum machine learning, in particular about generalization in quantum machine learning. So, I will better define it carefully. Then I will talk about our main result, which is quantum machine learning is not that data hungry as we initially thought. Our result is framed in terms of rigorous mathematical theorem, but instead of going through the proof, I will show you some examples of its applications. I will talk about recognizing quantum phases of matter. I'll talk about quantum compiling, and then the way we can do it classically much more efficiently than what was previously believed. I'll also talk about learning quantum dynamics and fast-forwarding real-time simulations. All right, so let's start with something simple. All right, we have classical machine learning, very simple task of recognizing handwritten digits. All right, so I'm training my neural net on many examples of handwritten digits. So I'm asking different people, right, to draw their versions of zeros, 4, and so on, and I'm using all those examples to recognize those handwritten digits, right? So I have, at this very pictorial level, I have neural net that is spanned with some number of variational parameters that I'm training to recognize those digits, right? So, after successful training, when I applied my neural net to a picture of handwritten 0, a neural net, I expect, will return number 0. When I apply it to handwritten digit 4, it returns number 4, and so on, right? So after successful training, after I'm done with optimizing my cost or loss function, right, I will I'll be able to say that my neural net works on most of the training data points that I have. It doesn't obviously have to work on all the points perfectly, but for most of them, right? But what I really want to achieve is the generalization, right? Obviously I cannot train on all possible ways someone can write, say, at digit 4. I want my network to generalize, so I want to apply it to unseen, say, picture of handwritten digit 4, and I want still to return correct label, right? So that's called generalization. And as you can imagine, this generalization or the generalization error is a measure of how well my network works on unseen data, right? So formally, generalization error is defined as the difference between testing error and training error, right? So testing error is the error that I make on unseen data, right? So on all the points outside what I train on, and training error is the error that I made during training, right? So on the data here inside that circle here, right? So intuitively, the generalization error, I wanted to make it as small as possible, obviously, right? So I want to train on some small number of examples, but I want my network to work on unseen data. So I want the generalization error to be small. And then I want to discuss the difficulty of making the generalization error small, right? And the difficulty, as you can imagine, will be a function of a problem, right? More difficult problems will be harder to make the generalization error small, right? It will depend on the size of the training data, type of the training data, and so on. Okay, so that was classical machine learning. How do we make it quantum? So I will replace classical data, so those classical examples of handwritten digits, with quantum states, right? And what I want you to imagine is that those quantum states live inside quantum computer, right? I've been running some experiment, and then these are the outcomes of that experiment, right? I've been running some simulations, and I have some example quantum states laying around. So this is the first thing that I do from going from classical machine learning to quantum machine learning. I replace the type of the data, right? I no longer work with handwritten digits or pictures, of cats and dogs. I have inherently quantum states, and I really mean quantum. Those should be outcomes of some quantum processes of interest. We will not be thinking about using classical data that is encoded in quantum states, right? So think about this as some outcomes of some experiments. Another thing that I do is I replace a neural net with variational quantum circuit that you see here, right? So I have some number of gates, and some of them are parameterized, right? So the typical setup is that I have some C nodes that are not parameterized, and I have 1 qubit gates that contain some number of variational parameters that I can tune, right? And in the example I'm showing you here, excuse me, in the example I'm showing you here, I'm classifying states, right? So you can imagine that this training data contains of states that are either ferromagnetic or anti-ferromagnetic, all right? And I'm training my neural net to classify those 2 quantum phases, right? So the idea is that when I apply my variational circuit to a ferromagnetic state, the measurement will return a label ferromagnet, right? When I apply to anti-ferromagnetic state, the same neural net will return a label anti-ferromagnetic. Obviously, quantum computer doesn't work like that, right? It returns, zeros and ones with certain probabilities. So, I have some encoding, right? I would say that, I will measure, say, 1 qubit, and then if the probability of finding 0 is, say, larger than half, I will attach a label anti-ferromagnet, and if it's smaller than half, I will attach a label ferromagnet, right? So, this is how I organize my training, right? I will define my cost function such that all the labels for all the training data points are as accurate as possible. I will optimize my parameters to lower down the cost function, but what I really want to achieve again is the generalization, right? So I don't want to train on too many states. I want my network to generalize. So after the successful training, when I apply my neural net to unseen example of, say, a ferromagnet, I want my measurement to return a labeled ferromagnet. Right. So just to clarify, the optimization is done on a classical computer in the same way that classical machine learning. Right. What happens on a quantum computer is that I store my data on a quantum computer. I evaluate quantum circuit and I perform the measurement. Right. Based on the outcome of that measurement, I'm computing gradients. Whatever I do to optimize parameters theta to lower down my cost function. All right. Okay. By the way, if there are any questions, feel free to interrupt me during my talk. I'm happy to answer all the questions as I go. All right. So I don't have to convince you that in classical machine learning that generalization has been extensively studied, right? So upper bounds on the generalization error has been derived from many examples. Now we know how much data is needed for good generalization, right? Depending on the problem type, type of the training data we have, size of the training data, type of training, and so on. And it goes without saying that this has been extremely successful in the areas such as computer vision, natural language processing, and so on. So this works great on a in classical machine learning. In quantum machine learning, this hasn't been studied that much. So the generalization properties have not been studied before. There were some numerical examples, and then if anything, they pointed to some troublesome, I should say, initial conclusions. And if you think about it, you may come to conclusion that in quantum machine learning, we may need exponential amount of training data, right? So if you think about it, we have n qubit gates, right? Those are spanned by roughly 2 to the n parameters. Our Hilbert space is exponentially large. So maybe we need exponentially amount of training data. So if that was in general true, then indeed that wouldn't be good. We would be in trouble. But this doesn't have to be true. I wouldn't be giving this talk if that was the case, right? So in practice, or the first thing to observe is that in practice we only need we will be working with shallow circuits. Here shallow means polynomial in the number of qubits. So if you think about it, this is the only setup that actually makes sense quantumly, right? So we want to work with circuits that are polynomially deep in the system size. If we actually think we need exponential or exponentially deep circuits, then quantum computers are not useful for this task, right? We want to run our circuits in polynomial time. So that's the first observation, that the depth of the circuit is going to be at most polynomial in the number of qubits. That's going to be my assumption, that the depth of the circuit here denoted by capital T is going to be polynomial in the system size. More precisely, actually, the number of parameterized gates is going to be polynomial. This is what matters from the theory point of view. So under those assumptions, we've shown that the generalization error, so the difference between testing error and training error, is bounded by the function that scales in the following way. That bound for the generalization error grows as a square root of t, where again t is the number of qubits, and it's proportional to inverse of the square root of the size of the training data. All right, so this should agree with our intuition, right? So the harder the problem, think about this classification task. The harder the problem, the deeper the circuit has to be, to say classify some complicated phases of matter, whatever. So the more gates I have, so the larger T, so the larger the generalization error, or the harder it should be to make generalization error small. On the other hand, if I fix capital T, so I work with a fixed depth quantum circuit, then I will be able to suppress the generalization error by adding more states into my training data, right? So I put more and more states, I train on more and more examples, and I can suppress the generalization error via that bound that we prove. All right. So let me recap here. In this paper, we've shown that the generalization error can be suppressed with small amount of training data. All right. So a proper way of saying that is polynomial circuits require polynomial training. Or in other words, polynomial training is sufficient to suppress the generalization error for polynomially deep quantum circuits. So now we have rigorous proof of that fact in our paper. And you can look up the details if you're interested. What I want to say here is that this theoretical bound is loose. So this is kind of the worst case example. It will always work, right? But in practice, what we see is because of certain symmetries of the problem, because every problem is somehow special, there are some simplifications that the method can automatically discover, that that amount of training is even smaller, right? So in the worst case, it should scale as t, just neglecting this logarithmic factor. But in practice, you will see that this is actually much better. All right, so even smaller amount of data is required. All right, so the first example, I will go over classifying quantum phases of matter. Right, so imagine that our task is to tell apart different phases of matter. Right, so imagine having some experiment, right, that is generating states, and you want to know what type of state you are dealing with, right? Is it ferromagnet? Is it antiferromagnet? Is it topologically ordered state? Is it trivial state? Things like that. So this is what we are doing here. I'm selecting some small amount of training data. I'm training my my parametrized quantum circuit on all those examples, and what I want to achieve again is the generalization, right? I want to show, or I want to use very few training data points in the training process, but I want to make sure that this network will generalize well, right? So when I apply it to previously or to unseen example of, say, ferromagnetic state, this will actually classify that state properly as a ferromagnet in this case. So that's the Hamiltonian we were working with. So this is one dimensional cluster Hamiltonian. You see that I have two coupling constants, J1, J2, and the phase diagram is reach, as you can see. There are four different phases of matter. There is symmetry protected topological phase. That's phase number one. It's somehow split into those two regions, which from training point of view is not necessarily good. Then we have ferromagnetic state. That's phase number two. We have this anti-ferromagnetic and also trivial state in the middle. And as you can see, that ferromagnet is achieved at large positive value of J1, as you can guess from Hamiltonian. Then for large negative values of JY, we have anti-ferromagnetic state. All right, so this is our parametrized quantum circuit, our ansatz for that quantum classifier. And for that, we will be using quantum convolutional neural network. And this is some ansatz that is built with layers. So, here I'm showing you example on 8 qubits. The number of layers is logarithmic in the system size. So for 8 qubits, we only have 2 layers. So each layer consists of 2, so to speak, sub-layers. We have convolutional and pooling layer. So, this may, or this looks like multi-scale entanglement renormalization ansatz that is used in computational condensed matter or in computational quantum many-body physics. And the idea is similar. So this convolutional layer, acts as disentangler. If you've heard about multi-scale entanglement renormalization ansatz. So the job, or what this convolutional layer is achieving, is disentangling that state such that the pooling layer is more efficient at compressing the data. So as you can see, that pooling layer, so this blue gates, that layer maps a system of n qubits into a system of n half qubits, right? So if you look here, this layer 1 here maps a system on 8 qubits into a system of 4 qubits. Now, half of the qubits are traced out, right? So you can think about it as compression layer, or as some kind of filter, right? That gets rid of unimportant information, right? That leaves only the information that is relevant from classification point of view, right? So that's what this layer tries to achieve. And the convolutional layer, you can think about it as helping the pooling layer achieve its task more efficiently. So it's disentangling in a sense such that the pooling layer is getting rid of the information that is irrelevant more efficiently. All right, so that's our ansatz. And then the way it's going to work is that we'll apply it to a state, and we'll measure 2 qubits. We have 4 distinct phases of matter, so we need 2 qubits to encode that 4 labels, right? So I will apply my convolutional layer, my convolutional neural network to a state, and then I will measure 2 qubits, and then I will look at probability of observing a given output, right? Either 0, 0, 0, 1, and so on. And then I will say that I will classify my state as symmetry protected topological if I see 0, 0 outcome as most probable outcome, right? Then 0, 1, if 0, 1 is most likely, then I will call it ferromagnetic, and so on. Obviously this is arbitrary, right? I could label this whatever I want. I have this gate here that makes sure that I allow myself to arbitrary 2 qubit operation to match that outcome into the one that I've chosen. All right, so this is our testing. So I'm choosing some small number of ground states pretty much randomly, but it's almost randomly. I just want to make sure that all the phases are properly represented, right? So the way this was done is that I chose 3 points from phase number 3, 3 points from phase number 2, and so on. So there shouldn't be a bias, right? So this is the only thing that I'm putting by hand, and the rest is essentially random. So that's my training data. So what I do is that for all those points, for all those values of J1 and J2, I obtain a ground state of the Hamiltonian, right? And then I'm training my convolutional neural net to return correct label for most of the states. All right. So after successful training, after I reached sufficiently small value of my cost function, I'm testing my neural net, right? So now I select I think, around 10,000 values of J1, J2, so 10,000 ground states, and I'm testing one by one whether my network returns correct label. All right, so the blue color represents correct label, and the red one is incorrect. And as you can see, in the vast majority of cases, I achieve correct classification, right? Only few points near the boundary of phase are incorrectly classified. So if you think about it, and this is what you should expect, right? So the points deep inside the phase are easier to classify, right? They are far away from phase boundary. The correlation length is small. It should be easier to classify, and this is exactly what we see. So only the points that are close to the phase transition may be misclassified, right? So there are two arguments to support that idea. So the first one is that those phase boundaries were obtained for infinite system, right? So this is analytical result. It's valid in the limit of infinite system. Here we have 16-qubit system, so not infinite. So those phase boundaries will be shifted, right? So there is no mystery, right? Or we shouldn't really expect that will exactly match that phase boundary. Another point is that the classification is getting harder the more entangled my state is, right? So if I approach the phase boundary, the state gets entangled, and this simple neural net that I've shown you is having more and more trouble recognizing the phase, right? So this could be fixed by let me go back to this ansatz, by adding more convolutional layers. So this convolutional layer, if you heard about tensor networks and then multiscale entanglement, the normalization ansatz in particular. So the number of convolutional layers acts as the bond dimension in tensor networks. So this is the simplest example. I could increase the power of that convolutional neural net by adding more layers of convolutional layer before I apply a pooling layer. So that was the simplest example, but it worked well already. Okay, so let me show you more quantitative data. So I'm essentially analyzing the data that I showed you before. Here I'm showing you testing accuracy versus training accuracy. Here accuracy is defined as the percentage of correctly classified points, right? So 0 is the worst, 1 is the best. We have four phases, so the accuracy of 0.25 could be achieved just by guessing, right? So anything above that is non-trivial. So what you see here is essentially linear dependence, between testing and training accuracy, and the slope of that linear dependence grows with the size of the training data, capital N. Right, and this is exactly what we want to see. This is what our theorem says, which is the more training data I have, the easier it is to achieve good testing accuracy. Right, and this is what this plot shows. We were looking at different system sizes, right? So here I'm showing you results from 8 to 32 qubits. And we were testing, how the size of the system, so how the number of qubits impacts the size of the training data that is required to reach good generalization. And what we've seen that there is essentially no dependence, right? So it's as easy to work with large system, as with a small one. And this is what you kind of expect for this particular problem, right? So most of the states that we are looking at are shortly correlated, right? So the overall system size doesn't really matter that much, right? So because we just need few layers to disentangle the state and to classify it correctly, right? So the theorem predicts that the the size of the training data should grow at most logarithmically with the system size. What we see in practice is that constant amount of training is sufficient to achieve good generalization error. All right, so let me move to another example, which is quantum compilation. So the example you've seen was fully quantum, right? You know, we had quantum states, we had quantum neural net, we were training on quantum computer to analyze quantum data, right? Now, I will show you that a similar idea could be used to purely classical task. So, you know, this should be performed on classical computers. This is a task of quantum compilation, which is you give me a unitary, in this case, it's quantum Fourier transform, or you give me a circuit, and my task is to compress this circuit, possibly approximately, as much as possible. You know, I don't have to convince you that this is an important problem for near-term quantum computers. We want to make our circuits as shallow as possible, right? Because, you know, every gate introduces some error, right? When it's evaluated on a noisy quantum computer. So the task is to compile my circuit so it's using as few gates as possible. And the way we're going to do it is via quantum machine learning. And our approach is very different from typical compilation tasks. And you know, this compilation is ubiquitous. You know, every single software stack you download from every company, there is some compilation tool, right? Because, you know, we want to have our circuits as shallow as possible. So, you know, we need to compile our circuits very often. So we are doing it in a different way, and as you will see, it's very efficient. So we want to think about compilation as a quantum machine learning task. All right. So, you know, I'm going to select some hopefully small training data of essentially random quantum states. Those will be inputs for my quantum circuit, right? I will train my variational quantum circuit here such that it will match the action of the unitary that I'm compiling on those trial states. All right, so that's my cost function, right? I want to minimize the distance between the true action of the unitary that I'm compiling on training states and whatever my variational ansatz gives me at a given iteration, right? So, you know, once my training is successful, right? So, you know, once I bring that cost function to some small value, we will be able to say that the compilation is valid on all the training data, right? Or via linearity on the subspace that is spanned by states that I have in my training data. However, because of generalization, we will be able to say that this compilation also works on states that are outside the training data, on arbitrary state from the entire Hilbert space, right? So, you know, this is where the power of that method will come from. You know, I won't have to train with all the states from the Hilbert space. It will be enough to train from using very few states inside that Hilbert space, and this will be enough to compile the entire unit train. All right, so this sounds good. Let's see if this actually works. All right, so here I'm compiling this quantum Fourier transform, and I'm showing you on that plot the size of the training data that is required for full compilation as a function of the number of qubits. All right, so, you know, as you can see, I'm reaching 9 qubits here, and the size of the training data is around 15 or 20, right? So much less than the dimension of the Hilbert space that I would you know, I would have to use that many data in a naive compilation, right? So the size of the Hilbert space here is, you know, over 500, and I'm showing you that you know, you are essentially fine with 20 or 25 states, right? So, you know, note that there are two lines here, the red one and the blue one. And so far, what I haven't told you is that this generalization is probabilistic, right? So in other words, it may or may not work. And this is kind of confusing, you know, if you think about it. But so let me try to explain that. So the generalization is probabilistic in a sense that there is a finite probability, smaller than 1, that once you achieve small training cost, there is finite probability that the small training cost will translate to small testing cost or to small testing error. All right, and that probability is a function of the size of the training data that I will explain later on. So you know, here you see those two lines. So the red one corresponds to almost certain compilation. So you know, most of the runs are successful. They translate into successful compilation. And the blue line corresponds to rare but still possible generalization. All right, so you only see this from time to time, but it's possible to observe it. So you know, in both cases, we have more or less linear dependence, you know, between the size of the training set that is required for that compilation as a function of the system size. So you know, as you can see, this is already much better than the exponential cost or the exponential training size that one would naively think that is needed, right? We don't need exponentially many. We only need linear. However, that was in the worst case of choosing computational basis state as your training state. So this is by far the worst case. You know, we could do better by choosing random training. So, you know, if you choose hard random training states, you can show that you can achieve the compilation with as few as 4 or 3 states. And that number does not depend on the system size. So now what I'm showing you here is that if you choose your training states carefully, you can compile 9-qubit unitary with as few as 3 or 4 training states. And you know, keep in mind that in a straightforward, naive compilation, you'll need over 500 states, and I'm showing you here that with 3 or 4, you can achieve the same task. So it's much cheaper. All right, so you know, here I'm explaining this probabilistic nature of compilation in some more detail. By the way, how much time do I have? I can't hear you.
15 minutes.
15 more minutes. Okay.
Yeah.
All right. Sounds good. Yeah. So, you know, here I'm looking at this probabilistic nature of compilation in some more detail. Here I'm showing you the distance between true or the target unitary, capital U, and my variational best guess as a function of the size of the training data for many optimization runs. So, you know, here every circle corresponds to a successful training. By successful, I mean I minimize the cost function. And keep in mind, the cost function only minimizes the distance on selected training states, right? So, you know, this is what I'm doing. I have many simulations, you know, as you can see here. And what happens is that if the training data size is too small, then despite the fact that all those points represent successful training, they all fail when I look at the full compilation, right? I look at the full unitary, I compare it with my exact quantum Fourier transform, and it's anywhere near, right? You know, this error is as large as I would get for essentially random guess, right? But what happens is that once I start increasing the number of training states, it is more and more likely for compilation to work. So that's the probabilistic nature of it, right? So if I take too few training data points, it is very unlikely for the generalization to work. But as I increase my training data size, it is more and more likely, and eventually it is virtually guaranteed that every run I have, every successful training I have will translate into successful generalization. All right. So so here's another way of explaining that probabilistic nature. Here we are looking at testing error as a function of inverse of the training error. So as I train my my quantum circuits, I minimize training error. So I'm moving from left to right, on all those panels, right? So I'm minimizing training error. However, small training error does not translate into small testing error if my training data size is too small. So for example, here you see that, when I have 17 states, despite successful training, I don't have a good compilation, right? So testing error is still very, very large. But as I keep adding more and more states, then I'm more and more likely to see a good compilation, right? And another thing that you see is that our optimization method is very reliable, right? So here I'm showing you every single optimization run that we've done. All right, so there is no post selection. Every run was successful from the training point of view, right? So every run reached very small values of training error. I think the threshold was something like around 10 to minus 10. All right, so to achieve that, we are using, let me say, some sophisticated optimization tools. So this is not just optimization over continuous variables. We are optimizing over structure of the ansatz as well. So we call that variable ansatz, VANS in short. This has been coded up by one of our students, Matthias, and it is available from his GitHub. The way it works is that we are optimizing over type of gates, over layout, so position of gates. We are removing gates, adding gates, and also optimizing at the same time over continuous parameters. So over all angles that are present in one qubit gates, right? And the reason we are doing this is that with this method, we can find solutions that contain as few variational parameters as possible, which is good for generalization. As you remember, the more variational parameters I have, so the larger capital T, if you remember, then the larger training set I need, right? So imagine doing this just with say hardware efficient ansatz, right? With hardware efficient ansatz, I have as many gates tightly packed, as possible. I have huge number of variational parameters. This might be good from, say, reaching a given state point of view, but it's not good from generalization point of view. From generalization point of view, I want to have as few gates as possible, and this is one way to achieve this, right? So I'm optimizing in the space of circuits, right? I'm moving gates around, adding, removing, and also optimizing over continuous variables at the same time. All right, so we're satisfied, or we've been encouraged, by those results, and we increased the system size, even further. So here I'm showing you a compilation of 40 qubits, 40 qubit quantum Fourier transform using only 2 data set points, right? So this is almost as small as possible. We tried with 1 training data point, obviously, but it didn't work. However, it works perfectly fine with 2 training data points, which, if you think about it, it's kind of ridiculous. We have 40 qubits, and 2 to 40 is over a trillion, right? It's a huge number. With standard techniques, I would have to match the action of my target unitary with my variational circuit on every single state from that set of 1 trillion state, right? Here I'm telling you that it is enough to train with 2 states, and you achieve the same quality of the compilation. right? If we have time later, I can talk more about the details of that calculation. But let me move to another example, which is learning quantum dynamics. So here, the task is to learn the parameters of some unknown Hamiltonian by studying the evolution of product states, under that Hamiltonian. So the task is that you give me that Hamiltonian, you promise that it has that form, right? So I have ZZ, nearest neighbor interaction, I have XX interaction and some field. What you don't tell me is that is the values of those coupling constants ABC, right? So my task is to figure it out by looking at the evolution of product states only. Okay, so the setup is very similar. We have some training data, which now consists of product states only, right? I don't allow myself to use entangled states, so it's no more random states. I'm only working with product states. All right, and then the task is to figure out those parameters, and we will use the generalization bound to guarantee that the circuit that you see here, that this trained circuit will work or will reproduce the correct dynamics on arbitrary state outside that training state that I have. All right, so as you can see, I'm making another step in this generalization, right? So previously I've been telling you that it is enough to use very few training data points or very few training data states, right? Now I'm telling you that it's okay, or it's enough to take very few, very simple training states. They don't have to be random. It's enough to take product states, and you will achieve the same generalization as before. All right, so it's another step in simplifying the training process. It's no longer just about the size of the training state. Now it's about the type. It's enough to train on simple states. All right, and here I show that this actually works. All right, so I'm learning that those parameters in Hamiltonian for system sizes up to 12 qubits just by using two product states. All right, and this capital L now measures the depth of the circuit, and the larger it is, the more accurate my prediction becomes. All right, and we see two things here: the so-called in distribution error. Here I call it in distribution testing, which means that I train on product states and I test on other product states. All right, and as you can see, this type of generalization works well, and that's that dotted line. However, what's more important is that out of distribution generalization works. So I train on product states, but the testing works on arbitrary state. Okay, and this is relevant, for example, when you're training on actual noisy device. So imagine you have some process running on a quantum computer, and you want to match the Hamiltonian of that process, right? You identified some interactions, but you're trying to fix the coupling constant. So exactly what we've been exactly what I've been showing you 2 slides ago. So if you don't know about this out of distribution generalization, you may think that in order to train your neural net, you need very complicated, essentially random input states. In that scenario, you will find yourself on this blue curve here. So despite expensive training here measured in number of shots that are spent during training, the testing error does not go down. It actually becomes worse, and the reason for that is that those initial states that we've been preparing are too deep. They are too noisy. They introduce so much noise that the neural net cannot handle that, cannot extract the relevant information from such a noisy state. However, if you're aware, so to speak, right, of this out of generalization error, you know that it's enough to train on product states, and product states, are trivial to prepare, this is just a single qubit rotation, so so they are essentially noiseless, right? So you're not picking almost any noise, and you can train and find the parameters as shown by this red curve. All right, so very quickly, I'll go over a final example, which is variational fast forwarding. So that's the method to evolve initial quantum state psi of 0 according to a given Hamiltonian on a noisy device. So here this arrow represents a simulation time and also the time that is spent on a quantum computer, right? So the device is noisy, so we should really think about it as having a finite window, this red region here, in which we trust the results coming out of the quantum computer. If our circuit is longer than that, then it picks up too much noise, and we shouldn't really trust that result. So whatever we do needs to fit in this red region here. The standard method of evolving the Hamiltonian is trotterization, in which you trotterize a single time step, and then you repeat that time step as many times as you need. As you can see here, with very few time steps, you can go outside that coherence time. So outside that safe red region, and your simulation then becomes worthless. So what we propose instead is to approximately diagonalize one time step. And if we manage to do that within coherence time, then we can study longer time evolution with essentially the same circuit, or with the circuit with the same depth. All we have to do once we find that diagonalization is we just change the parameters of that middle circuit D. So we change the exponents in the diagonal circuit, and we can study the evolution, the much longer evolution with the circuit that has the same depth, right? So this is the algorithm that we proposed some time ago, and it works well, but there are some issues that could be improved, right? So it requires doubling the system size, right? So if I'm studying n qubit system, I need 2n qubits to find W and D in that expression here, right? I can decrease that qubit overhead at a cost of exponential training set, and then obviously this is suboptimal, and as you can guess, we can improve that with our generalization bound. So we will treat the task of finding W and D as a compilation task. So I'm gonna view this as compiling E to minus I H delta T into this very particular form. So it's no longer, so to speak, free compilation to whatever circuit I want. The circuit that I have to compile my trotter step has to take this very peculiar form, all right? But it's still a compilation task. Maybe the optimization is a little bit more complicated, but still my task is to find gates in that decomposition. So I'm using the compilation tool that you've seen before. I have some training data, and the hope is that with very few states, I will be able to find compilation that works on arbitrary state in the Hilbert space. Right, and this is exactly what we see. So here I'm showing you fast forwarding for 4-qubit Heisenberg system, and as you can see, we can achieve very good compilation quality with as few as 5 states. And the inset in that figure shows that once we achieve that compilation, then we also achieve fast forwarding. Right, so I can track my real-time dynamics very accurately for as many as 2,000 time steps, right? So this is way beyond what standard trotterization can do. And this has been achieved at a very low cost as well, with only few training data points. Here I'm showing you that This could be extended to XY model on larger system sizes. So, here I have 12 qubit simulation, and what's needed for the compilation is a single product state. So that's sufficient to lower down the generalization error such that we achieve very good fast forward, which is shown here in that inset. So here we can simulate this system very accurately up to something like 1,000 time steps, which again is well beyond what's possible with standard techniques. All right, so here's a summary. So some take-home messages. Turns out that training quantum machine learning models, can be very cheap. Much cheaper than we would expect. We have rigorous proofs, that claims in our papers. And on the practical side, we can apply that theorem. We can apply those techniques to tasks like quantum phase classification, quantum compilation, real-time dynamics, and so on. All right, with that, I thank you for your attention, and I welcome questions if we have some time. I believe I'm required to present this slide for a few seconds if you are recording this talk. Yeah, are there any questions?
The session is open for questions, comments, any queries that anyone might have.
Can I ask 2 questions?
Please, please. Go ahead.
Yeah.
Sure.
Thank you for your talk. First question, what kind of verification techniques you use to verify your output results?
Yeah, so right, so you're selecting some states, some small number of states, and then once you are done with training, you select other random states, and then you are testing your task, whether it's compilation, right, or it's classification. It's in most cases it's just random states.
Thank you. So second question, could you please name the software packages you used in calculations considered in your presentation?
Yeah, so that's this VANS package. So this is one thing that we use. So this is available. There is also QFactor that I'm not mentioning here, but it's an optimization tool that I use specifically for that compilation task. And the rest is kind of homemade simulation techniques, tensor network algorithms, which is not yet available.
Thank you.
So if you're interested, I can describe the algorithm in detail. I think we are doing a good job actually in those papers. In some appendices, we're trying to go into details. But if you need more details, I'm happy to talk to you, because the code is not fully available yet. Right? There are some pieces, bits and pieces, in this VANS algorithm, in QFactor, and in some other places. Okay. And the generic tensor network packages, that you can download. Yeah.
Sometimes it is very difficult to
training set and the quantum circuit. So no matter what you do, you cannot break them, because your answers is symmetric and you are training on the right data, so to speak.
Thank you.
Let us all thank Professor Cincio for a very interesting and very thought-provoking talk on his work